Hello all, I hope you are able to hear my voice. Awesome. I hope you all are staying safe and following COVID-19 safety rules at your side. My name is Sayam Kumar and this talk is for PyMC 2020. I'm going to be talking about demystifying variation inference. First of all, I want to thank all the organizers, executive chair members, all the volunteers out there for putting up so much effort in shaping this great conference. This is all going to be a fun day. A little bit about myself. I'm pursuing my bachelor's in computer science in South India. I've spent a great summer with PyMC devs and I contributed towards adding variation inference methods in PyMC4. So whatever I have learned over a period of past 3-4 months, I decided to summarize here as a small talk. I hope you all enjoy it. I've also included the link of the GitHub URL where you can look upon the slides in the Jupyter notebook. You can also look upon my Twitter and blog if you wish like. Let's get started. So today's agenda will be, I'm going to be kickstarting with what base rule is so that everyone is on the same page. Then I'm going to talk about why at first do we need variation inference and how this particular fancy term is connected to information theory. Then I want to talk about what approximations we can make use of in variation inference. Mm, it's a bit of always a hassle when we are directly implementing variation inference in tensor libraries. So I'll make you walk through some out-of-the-box implementations in PyMC3 and 4. Ultimately, I'll be discussing about some model diagnostics that can help you use variation inference in your own use case. Okay, so the main idea behind Bayes' theorem is it helps in modeling the underneath data generative process for whatsoever parameters we aim at calculating them. We define them as random variables and we call them as priors. And when we actually feed in the data, we compute the likelihood term. We are actually interested in computing those parameters that can actually fit the data. And this particular term is called likelihood. Bayes' theorem helps in connecting the posterior term in terms of likelihood and priors, but it's not quite uh, easy to compute the posterior term because of this devil denominator. The probability of data here is computed by marginalizing out the effect of all the parameters, which is intractable most of the times. So this intractability of the denominator actually makes the posterior intractable. So that's why we resort to MCMC algorithms or variation inference approaches. Yeah. Uh, as an example, we wish to infer the mean and standard deviation for some normally distributed data. This will help us in giving underneath view of what goes on there in variation inference. We'll be making use of TensorFlow and TensorFlow probability libraries to actually help us getting our mathematical equations transformed into the TensorFlow and the Python code. Here I'm just generating 1,000 normally distributed data points with mean as 12 and standard deviation as 2 point something. And we wish to uh, model this data generative process and get back to this actual mean and standard deviation. Here we are actually defining the data generative process which might be going underneath. Since we know the sigma and the so-called the spread of the data is positively constrained, we can make use of exponential distribution. We can make use of any priors, but here I'm just using the normal one for the mean with location as mean as the standard normal one. I'm just passing these priors to the likelihood and then passing the data to compute the exact term. TensorFlow probability helps us in a better way connecting these priors and likelihoods to define our joint model. Yeah, it's a good idea to print out what actual graph looks like in TensorFlow. As you're going to see, the mean and standard deviation are just the free random variables in the graph, and the likelihood term actually depends upon the mean and standard deviation, which does mean we are actually on the right way. Uh, Now we are interested in computing the joint probability of the model, which is just the product of likelihood and priors. We can also safely say the posterior term right there in the Bayes rule is directly proportional to the joint probability. And most of the times, right now from onwards, we're going to be dealing with this joint probability. And this log term out there in joint log probability is due to the fact we are unable or we are not very much considerate when we deal with values which are close enough to zero. Because when we compute the joint probability, there can be a case the probabilities are close to zero and their product will ultimately will be close to zero. So that's why we're going to use a log term to actually split the product into the sums. Yeah, for certain samples for our priors, we're going to be calculating the log probability and passing in the data for the likelihood term. And for all those individual parts, we are calculating the log probability. And one good question to ask yourself is uh, how to handle the shape if any particular sample is of different shape with respect to the parameters of the model. Uh, there can be cases will be the shape errors. So the basic key idea is for all the parameters of the model, after we have calculated the log probability, we're going to be reducing all the dimensions of the log probability of all parts and then take the sum. And this will help us in actually generating a single number that represents the log probability of the model over some certain samples. Let's go ahead. Okay, since we have computed the joint log probability, we can run a Markov chain and draw some sort of samples. And these samples can be drawn out long enough to actually get to the exact posterior. But the question here is, can we do reasonable and can we do better in terms of space and time complexity? And that's how we're going to be talking about variational inference. Variational inference is not a sampling approach, it's an approximating approach where we are computing the posterior by an approximating distribution. And this particular distribution comes from a family of distributions that we aim at choosing one that's closest to the posterior. Since I'm talking about choosing a distribution that's closest, there is some sort of distance criteria involved. And that's how the variation inference gets connected to information theory. This particular term for measuring the distance between two distributions is called KL divergence, which governs how much bits of information do I need to distort more to get to the different distribution. So we do need to make our approximating distribution Q close to the posterior. So that's why we are aiming at reducing or minimizing the KL divergence or the so-called distance between the two distributions so that they get close enough. The KL divergence can be written in terms of the posterior and the approximating distribution. Since we are aiming at uh, minimizing the KL divergence, we cannot do so directly because it still involves the posterior term. How are we going to resolve it? The idea is we're going to just substitute the Bayes theorem and do some sort of refactoring which one can find in hidden cells to actually define a new term, and that particular term is called evidence lower bound or ELBO. This particular term is just calculated by refactoring. If you carefully examine this equation right there, the right hand side of the equation is just constant because we're going to fix the data for that particular model. Earlier we were discussing about we do need to minimize this KL term, but minimizing this KL term is equivalent to maximizing this ELBO because the right hand side is constant. So we have redefined our objective from minimizing the KL term to the maximizing the ELBO term. So that's what we're going to make use of in TensorFlow and define our ELBO objective. Let's go ahead. Yeah, so since we do need to maximize the ELBO to approximate our posterior, we do need to take its gradient and use some sort of optimizer, either by gradient descent or coordinate descent. Here is the point where whole of the Bayesian statistics gets connected to machine learning via variational inference because we are taking gradients and we are using some sort of optimizers to maximize a particular objective. Yeah, whenever we do need to differentiate or integrate with a huge number of parameters, we do consider approximating them. Earlier, we have approximated our posterior with respect to a distribution. Now we have approximated the gradient by Monte Carlo approximation. And just the idea is we have some sort of certain samples and we're going to compute the log probabilities and take the difference, which will ideally be the same if we have large number of samples. Yeah, here we're going to define it in TensorFlow. After we have drawn certain number of samples from the approximating distribution, we're going to calculate the log probability with respect to the approximating distribution and uh, the target log probability of the model as well. And then we're going to take the Monte Carlo approximation over the patches. This is how we're going to define our variational loss or the ELBO. Let's proceed ahead, but there is a warning. It's looking all good. We are working on building the right things. We have computed the samples and calculated its probabilities out. But one good question to ask is, what if a particular sample is not able to match the support of the distribution? Then uh, we'll not be able to compute correct log probability here. Since we were taking the samples from the approximating posterior, there can be certain cases those particular samples are unable to match the support of the distributions. So that's why we're going to make use of something called transformations to actually take our samples and match them to the support of the distributions by actually defining a proper transformation. Okay, the key idea here to consider worthwhile is we want to optimize our elbow in unbounded or unconstrained space, and we want our transformations to take the samples from the unconstrained to the constrained space to match support and correctly calculate the log probability. So if there is a transformation, an arbitrary transformation tree from unconstrained to constrained space, we calculate its log probability by just chain rule of differentiation and adding a constant term by the Jacobian of by the determinant of the Jacobian. Most of the times we were discussing about calculating the log probability, so we'll be taking the log probability in the log scale as well. Yeah, here is this directly translates to Python code and in TensorFlow. Okay, since we want a particular sample for exponential distribution to be positively constrained because it's sigma or the spread of the data, we can actually exponentiate that particular sample, and this will actually match this support of exponential distribution. For normal distribution is actually defined on the whole R scale, the whole real space. So that's why we'll not more interested into the support of normal distribution. So for the samples drawn out from the approximating distribution, we're going to be constraining them and we're going to be calculating the log probability over the constrained samples. Since we do need to add some compensating factor, uh, we do need to calculate the log of the determinant of Jacobian over some sort of event. We do need to make sure we are using the correct shapes, and the same idea of reducing the all the dimensions applies here as well. Since we are dealing with the log probabilities, we're going to be taking the sum, and this is how we calculate the transformed log prob in the constraint space for the samples drawn out in unconstrained space. I am focusing more upon the constrained and unconstrained because they can get quite tricky if one thinks more about them. Yeah, now there can be a case when the samples drawn out from the approximating distribution is not a single one. There are a batch of samples which we want to take out. So we'll vectorize our code using TensorFlow, and that's what main TensorFlow is meant for. We're going to be making use of vectorized maps or any other vectorization function in TensorFlow to actually make sure our batching semantic works correct and we correctly calculate drop probability for all the batch of samples individually. So here we have defined the base rule, and we have uh, defined what variation inference is, what's our objective is. Our objective is to maximize ELBO. We have also discussed what transform block prob is to actually match the support of distributions. Now the key idea is what's the approximating distribution I was talking the whole time. The key idea is we can choose anything we wish like, but we do need to consider them on the basis whether they are actually maximizing the ELBO or not. We can say we can use normal distribution because ideally uh, it has higher entropy levels and can get us uh, maximizing that particular ELBO term better. So we're going to be making use of normal distributions as an approximating distributions for the parameters of the model. The first assumption or the first approximating algorithm which we're going to see here is we're going to say our parameters of the model are uncorrelated. But this can be a case where uh, we do need to specifically model the correlation in the data as well. So there, this mean field approximation will not work very good. But since here the two parameters we are trying to estimate, mean and standard deviation, are actually free nodes in the graph, we can actually approximate them by normal distributions. And by defining our ELBO objective, we can get as close as to their underneath ground values. And that's how we're going to define uh, the normal distributions for each of the parameter of the model. We know there are two parameters, the mean and standard deviation. So we're going to be first taking out a sample. We're going to be removing the likelihood term. And for each of the parameter, we do need to approximate them by a normal distribution. Since the normal distribution is defined by a mean and standard deviation, we're going to be using TensorFlow variables, and these variables can help us get to their exact ground value. Also, one small thing to note here is since the standard deviation will be all positive, we do need to make sure that that's why we are also specifying a sort plus bijector over here. So here the idea is we have just computed the approximating distribution for all the parameters, assuming they are uncorrelated and approximating them by normal distribution. Yeah, so the loss function defined previously in terms of Monte Carlo approximation, we're going to call the function and we're going to apply the gradients. So here we are free to choose any optimizers we're going to think of, and we're going to run this optimization function as many number of times you're going to wish like. Yeah, so here I just combined all the different subsections we discussed so far. We defined a loss function in terms of maximizing the ELBO. We define our optimization function, and I also put up an array to make sure we are tracing out the loss at each step, so we can see if it is actually converged or not. And we are interested in computing, uh, the loss or approximating algorithm for those many number of steps which we pass in. So just a while loop to make sure uh, we repeatedly call the optimization function and take the gradients and optimize the ELBO. Yeah, I just define an Adam optimizer and call in the fit function to fit the target log prob with the mean field ADVI, which we have proposed earlier, some sort of 30,000 number of steps and with a batch size or so-called sample size as 2. Or since the approximating distribution we were posing for the posterior is actually in the unconstrained space, we do need to put up our bijectors again for the samples to actually match whatever we had earlier. So we started off with mean as 12 something and standard deviation for the normally distributed data as 2 point something. And I think we have uh, successfully modeled them with a good amount of accuracy using variation inference and mean field assumption. Yeah, here we are looking upon whether the laws traced out at each step, stacking them out has converged or not. Now one can see after some sort of 20k iterations, the elbow has been converged, and it's a good diagnostic to check whether elbow has been converged or whether the optimization has converged to a stable level. Then we can proceed ahead and continue with the iteration of data generative process. Okay, what more one can do inside the TensorFlow code, which we have seen earlier, since we are running optimization for those many number of steps we define, we can have a progress bar, a UI hack for our convenience. One can also look upon convergence checks to unnecessarily run the optimization for many iterations. One can think of whether the loss has converged, whether the gradients are related or not, whether the parameters uh, of the variational distribution have converged or not. If we do specifically aim at tracking the parameters out to ensure the probabilities are correctly calculated, we can also do that. To enable more data generative model, we can make use of deterministics that actually define if there is any constant multiplications over the priors before we're going to define the likelihood term. One more thing which you can think of here is, it's, as we know, it's not a good idea to put all the data into our memory. We can also define the mini batches, and then over those batches of data we run uh, any approximating distribution or the so-called variation inference. We do need some sort of minor tricks, but we do need to care if the batch semantics works all good for all these ideas. It will be quite a lot of things to implement, so that's why I'll now proceed to show you the out of the box implementations in PyMC3 or 4. Last time we discussed about modeling the correlations under the assumption they are all uncorrelated. We can go towards the extreme end and say, hey, are all the parameters of the model are related, and pose dense correlation metrics over all the parameters of the model. And doing so is called a full rank ADVI. There is some sort of compensation we can do over here by posing a rank diagonal update, which is called low rank ADVI, which can be seen as a compensation between the two extremes. Uh, Let me take some examples how we can use full rank and low rank ADVI in PyMC interface. Yeah, TensorFlow probability gives a better control how you can define approximating distributions, define the optimizers, run the optimization loop. There's a greater control. But if you're gonna talk about more and more functionalities, it will be quite a lot of hassle to do so in TensorFlow probability. So we're going to be making use of all the Bayesian machinery defined in 3 and 4, PyMC 3 and 4, uh, so as to just enable users focus on the data generative process and the inference drawn out from the inference algorithms. So this is how the model defined earlier for estimating the mu and sigma looks like in PyMC4. We're going to just define the normal distribution like before, the exponential distribution, and we just pass in both these priors for computing the likelihood and pass in our observed data as well for the likelihood. Yeah, well, you're going to see the number of lines of code has been reduced. We just need to define a model and call in the fit function, passing in the model, passing in the number of steps. We can also tweak uh, passing in the number of sample size, whether we want to use parameter tracking, progress bars, uh, convergence checks or so. So as I said earlier, one good diagnostic checks is whether the loss traced out from each iteration has reduced to a certain level or so. So you're going to see over 25k iterations or so, the elbow becomes constant. I think I was talking about maximizing the elbow term. Mathematically, it is equivalent to minimizing the negative elbow. That's what we are doing here in PyMC4 or TensorFlow probability. But if you're going to look upon how PyMC3 is implemented, PyMC3's variation inference uh, modules are implemented, they are actually maximizing the elbow. But the idea is same. Maximizing something is equivalent to minimizing the negative of that. Yeah, one interesting question here is one can think of what are some certain situations where we should use MCMC or where we should use variation inference. If we are not specifically targeted towards capturing correlation, we can kickstart using uh, mean field ADVI for our data generative process. One another thing to keep note is if we got tons of data, we can opt out to using variation inference because sampling we're going to take long enough. And if we can compromise to the accuracy, still we can use variation inference. A recent advances has been on uh, posing better transformations over the approximating distribution, not over the transform block prop. This has to be there. So the transformations over the approximating distributions to better approximate the posterior, and those terms are called normalizing flows. There has been great amount of research over there in this topic, and it will be quite good to explore as well. Now it will be all good to discuss about hierarchical modeling as an example of variation inference in PyMC4. We are considerate towards modeling the radon levels for a particular state, that's Minnesota. There are two uh, priors information which are given to us. One is we are given the measurement either in the basement or the first floor for that particular house, and we are also given the measurement of uranium level which we can make use of at a particular county level. So this is how our data generating model looks like. We're going to be making use of a hierarchical model one. The main idea behind hierarchical model is uh, we assume the samples of the data are generated from a population, and a population has uh, certain parameters, the mean and standard deviation. If we assume the parameters, if we assume the population is normally distributed, here we are also trying to capture the correlation, if there is any, of the intercepts and slope of individual counties. And for modeling the correlation, we are making use of a multivariate normal distribution. We do consider computing the covariation matrix in terms of its lower Cholesky triangular factors, because the correlation matrix is a positive semi-definite one, and it's some sort of n square times computation when we are dealing with correlation matrices. When defining in terms of either lower triangular or upper triangular, we just reduce uh, the amount of operations we do need to perform. Yeah, here is how the particular model translates into PyMC4. For generating random correlation matrices, we define LKJ priors, and to correctly transform the samples from the approximating distributions into the support of LKJ priors, we make use of a transformation called correlation Cholesky from TFP. PyMC4 is actually implemented on top of TFP, so everything we can make use of. One interesting thing to note here is ideally the transformation for a particular distribution is actually implemented in the class itself, in the class of distribution itself. But actually it's not currently there in the code base of PyMC4. So that's why we are specifying manually. Yeah, as I said earlier, for hierarchical models, we do consider the parameters are coming from a population with some parameters. So we define uh, the mu A and mu B as the parameters of intercept and slopes, and then we do try to model if there is any correlation by MV normal distribution. We do measure the mean by actually taking out those particular indices and correctly computing the mean, just set up an error rate, and that's how we're going to define correct likelihood. So it's a bit of complicated model if we're going to see at the very first glance, but ultimately we are aiming at computing the correlation, if there is any, between the intercepts and slopes of the so-called counties or the groups. Yeah, since we are aiming at computing some correlation, uh, we can compute both mean field and full rank ADVI samples. Here I'm arbitrarily running the optimization loop for 25k iterations, and for a better convergence I'm using a higher sample size. One can tweak these things out. Yeah, earlier I was discussing we do need to consider uh, factoring out the correlation matrix into the lower triangular Cholesky factors. So after we have the samples in lower triangular Cholesky factors, we do need to get them back. So here I'm just doing matrix multiplications to actually compute the exact correlation matrix between intercept and slopes. Here we are just considering if full rank ADVI is able to model some sort of correlation or so. As you can see in mean field ADVI correlation matrix, it's actually the identity one, because earlier we were in the assumption all the parameters are uncorrelated. Now in full rank ADVI samples, we can see there is a slight correlation in the intercepts and slopes of the individual counties or groups. But we can safely ignore because that's not a great correlation. Yeah, I'm gonna show this figure because to demonstrate the power of hierarchical modeling, it's important because for a certain number of counties or groups where we do not have enough data, we're gonna fit the model, and we're gonna approximate the parameters for those particular counties or groups close to the population parameters. So these, you can see these lines are actually approximating towards or going close towards the parameters of the population. If we have more enough samples from a particular county or a particular group, then we are more confident towards modeling them independently. If there are not enough samples, we're going to be going more towards the parameters of the population. A particular integer right there is important to us because it's denoting how big enough is the flattened shape of the parameters, and then we can pass this value to the low rank ADVI. For the rank that is very close enough to 1, we're going to safely say the low rank update will be close to the mean field ADVI assumption. And if you go close enough to the all flattened shape of the parameters, that is 176, we're going to compute, or we're going to represent the full rank ADVI one. So we can see, as I said earlier, the low rank is a midway of both mean field and full rank assumption. Yeah. So now I'll just discuss about diagnosing the model fit, or ultimately how variation inference can help in your use case. Yeah, it can be good if you want to run convergence checks with respect to the parameters, or with respect to whether the ELBO has been converged or not, so as we can get a better grasp and reiterate faster over the data generative process. If we can see uh, the ELBO has not been converged, we can just take the optimization loop and run it for further number of iterations. As we are approximating our gradients as well, we can uh, increase the number of sample size that are actually approximating that gradient. And then we can also take that particular distribution that has minimized ELBO in last few iterations. So these are just the basic and random thoughts that can help you use variation inference in your own use case. If one needs to do more tweaks and compare with MCMC samples, that will be really a good idea. So we are proceeding towards the end of the talk. The key takeaways from here will be uh, there is an approximating approach for finding the posterior. That's called variation inference. We define an objective in terms of ELBO. We do need to maximize it. One can govern and customize the degree of correlation we want in terms of mean field, low rank, or full rank one. If we have a lot of data and for reasonable accuracies, the mean field ADVI works all good. One can use the mini batch versions for efficiently implementing it. For using out of the box implementations and uh, actually focusing on data generative process, it's always convenient to use PyMC3 and 4. But if you want a better control, I would say use TFP. Yeah. Thank you for attending my talk. It's been a great time. If you have any questions, I'd love to hear any. Thank you.